All right, welcome to Monday. This is chapter 12. We will get through all of chapter 12 and into chapter 13 before the end of the year. So here we go. This is what the calendar looks like. We'll have a quiz next Monday. We'll talk about it on Friday, what's on it. We're going to roll right through. So we'll start chapter 13. And then that following week is going to be prep for the semester final. We have 5 weeks left. So the week that you don't see right there will be semester test prep. And then we'll take the semester test, and that'll be the end of the year. All right, here is your homework. Please copy down. All right, so if you remember last chapter, we just took the test. Last chapter was on area. Now we're going to move into three-dimensional objects, and that is volume. Okay, so 3 quick objectives. This chapter, we will do surface area, but it's going to be surface area of 3D shapes. And remember, area is measured in 2 dimensions. So even though surface area is part of a 3-dimensional shape, we'll still, when we do surface area, the units will be in square units. For those of you that had a good pre-algebra teacher, this is old hat to you. You may even remember the formulas for surface area. And also the volume. For most of the shapes we're going to deal with in high school geometry, you have seen these in pre-algebra as well too. Volume is measured in, or volume is a measurement of a 3-dimensional shape, and in, the units are in cubic units. So square units always for area, cubic units for volume. All right, good news, bad news for this chapter. It is lots and lots and lots of formulas and names and terms and definitions. But the good news is that there's a whole lot of formulas involved, but they're just formulas. So as long as you understand the formula, all you're doing is plugging numbers into a formula and chugging through a calculation. So for many people, they find, I mean, there's not as much logic based as the previous chapters. All right, here we go. So lots of definitions today. All right, the first one, hopefully you've heard this before, polyhedron. We had polygons, right? Shapes made up of segments joined at their endpoints. Well, this is polyhedron. So this is what applies to 3-dimensional shapes. So 3-dimensional shapes that are made up of polygons. So polygons, triangles, squares, rectangles, pentagons, hexagons, octagons. You put those shapes together, you join them at their edges, and you make these 3-dimensional shapes. They look like dice. And yeah, those are called polyhedrons. Those are primarily, there's a few ones, the sphere and the cylinder, cone, that don't involve polygons that we will be measuring as well too. All right, so what's the first one we're going to do? Well, the first 3-dimensional shape we'll be messing with is a prism. So a prism is a polyhedron that consists of 2 congruent polygonal bases. All right, so you're dealing with 2 polygons, like 2, I don't know, hexagons, and they will be connected using parallelograms. If that doesn't make much sense to you, well, let me show you a picture. So here are 2 congruent pentagons. 2 congruent pentagons. We join them, in other words, the sides of the pentagons, or the 2 congruent pentagons will be parallelograms. In this case, rectangles. Okay. And that shape right there is a prism. I know for me, even in high school, I heard the word prism. I always thought of the science thing, the little shape thing that makes rainbows. And yeah, that is a prism, triangular prism. But prisms come in all forms, shapes, and sizes. So this is a pentagonal prism. But there's rectangular, there's triangular, there's hexagonal. There's lots of different types of prisms. But the key here is that the bases, not necessarily the top and bottom, but the 2 polygons that are congruent, they face each other. Okay, and it could be top and bottom. It also could be left and right. So generally, we do draw the 2 bases, top and bottom. So here's a hexagonal prism, right? You never saw this in pre-algebra because they only gave you the prisms that stood straight up and down. But here's a slanted one. This is still a prism. There's lots and lots and lots and lots of terms here in definitions. So we're going to fill this whole page up full of definitions. Here we go. The first part of a prism is called a base, and these are the 2, and it's congruent. They have to be congruent. The 2 congruent polygons And they're also what define the shape. In other words, the shape is named after the two congruent polygons. So these two are hexagons, so this is a hexagonal prism. Okay? The sides of a prism are not called sides. You would think they should be. They're called lateral faces. And since it's a prism, the sides will always be parallelograms. Now, notice this particular one is absolutely parallelograms. Previous one were rectangles. Okay, and we'll talk about when that comes into play. All right, where the sides come together, the lateral faces come together, those make edges. Edges. If you were to run your finger around the sides of this shape right here, the sharp pointy part is called the edge, or in this case, since it's the lateral face, where the edges come together, that's why they're called the lateral edges. So these are the lines that connect the vertices, of the vertices. Boy, I can't get this right. The lines that connect the vertices of the bases, and they are parallel to each other. Notice all of those lateral edges are parallel to each other. Okay? All right. And the last one is altitude. It also could be called the height in some books. I do know we're going to use the height and altitude interchangeably. Altitude is the perpendicular distance between the two bases. Generally, we do call this the height in most math books, but as you go in higher level math, they use the word height and altitude interchangeably. Okay, so parts of a prism to continue. There are two types of main prisms, and we're not talking about triangular, rectangular, hexagonal. The first one is called a right prism, and this is where the lateral faces are rectangles. In other words, the two congruent bases are one above each other, or left and right, right? They literally stack up on each other, if that makes sense. But they are one above the other. Okay, it could be left or right as well too if it's turned on its side. The better or the more mathematical definition is prisms whose lateral faces are rectangles. Okay, and then you leave off the part where the two bases are oriented. Okay, so this says that the lateral sides are rectangles. These are rectangles. Further, the altitude is one of the, and remember we just said that's interchangeable with height. The altitude is one of the lateral edges. Okay, that is not true for a non-right prism. So I got a right prism on the left, right, and I have a non-right prism. Did I say that right? I have a right prism on the left, and I have a non-right prism on the right. Okay. So notice that the edges of the non-right prism do not measure the altitude. Okay, the altitude would be the perpendicular distance between the bottom base and the top base. Okay, so we do have a name for the non-right ones. They are called oblique. Oblique. So oblique prisms are the opposite of a right prism. Okay, in other words, the lateral edge doesn't form a right angle. On a right prism, all the lateral edges form right angles, and all the lateral edges are parallel to each other for both of these, right? Okay, makes sense? So where do you measure the altitude for the oblique ones? Well, sometimes you can do it from center of the bottom base to the top, but if not, then they offset it a little bit, but they're still just measuring the perpendicular distance between the two bases for both of these, for both the right and the oblique. Okay, so that's it for terminology for prisms. Today we're only going to be dealing with prisms, but we're going to be dealing with two measurements. One is called surface area, and one is called the volume. So we'll talk about the first calculation, which is surface area. Imagine this. Take any three-dimensional object, and it's basically the skin of the object, or what you can touch of the object. Sometimes I refer to it as if you took a can of spray paint and you spray painted the object, you would spray paint the outside of the object, not the inside. Okay, so surface area is the measurement of how much paint would touch the object, or in other words, how much skin it has. And you should remember of doing surface area in pre-algebra. Okay, so the surface area of a prism, now we're going to get a little bit complicated with terms and definitions. Don't panic, okay? First one is going to be called the lateral area of a prism. And this is just basically the measurement of the lateral faces. You take all the lateral faces and you calculate their area. We call that the lateral area of the prism. Okay. Well, that would leave off the bases, so then we have the base area of the prism. So these two terms right here, lateral area and base area, they are what make up the surface area of a prism. Now we have abbreviations for lateral area, LA for lateral area. Okay, that makes sense. And B, capital B, for base area. Of these two, the L period, A period is, it's kind of book dependent. Capital letter B, though, is always used for the base area of prisms. Now, remember, the base area is made up of two shapes, the two congruent polygons. So if it's a hexagonal prism, it's the area of the two hexagons. If it's a triangular prism, it's the area of the two triangles. Okay, so how do you calculate surface area? Well, it's basically those two things added together. So you take the lateral area, you add, well, not just one base area, you need to add the two base, because there's two bases, right? And that would give you, in this book they call it total area, TA for total area. A lot of books just put SA for surface area. Either one's fine. In my book, tonight for homework they're going to talk a lot about the total area, but total area is basically the surface area. So this book, if you see T period A, they're just talking about surface area. Kind of confusing, right? Okay. Well, we can't do anything in geometry without proving it, so this is your proof, and it's just basically some common sense. Okay, so if we think about the lateral area of a right prism, just a right prism, well, let's see, the lateral area would make, in this particular one, would be made up of what, 3 rectangles? We're talking about the sides here. So if we just cut the 3 sides, the non-yellow part right here, and we folded it out, it would look like that. Okay, well, think about this. That bottom edge of those 3 rectangles right there, well, that's basically the perimeter of one of those triangles. In other words, the perimeter of the base. Now, that would be true whether it's triangular prism or rectangular or hexagonal. The bottom of that right there would be the perimeter of one of those bases. Can you see that? Now, remember, right prisms, the sides are always rectangles. Okay? So any rectangle, the area of is measured by length times width. Well, the length in this case is the perimeter. So what would be the width? Well, the width would be the altitude. So I can tell you what the lateral area is of any right prism. It would be the perimeter of one of the bases multiplied by its altitude. Okay, so I don't know, maybe P for perimeter. And you would think that they would use A for altitude, but remember we already used A for apothem, so, well, this book goes back to the letter H. And I will say most books do this. So I would have preferred if they would have called the altitude the height, and there wouldn't be too much confusion. But, well, there's your formula. So the lateral area for any, now this only applies to right prisms, the lateral area for any right prism is the perimeter of one of the bases times the height. Okay? And then once again, since I just, by definition, the sides of a right prism are made up of rectangles, well, the proof of this, any rectangle is length times width, so it's lowercase p times h. So there's your non-proof proof right there. And we'll call this Theorem 12-1. And it says the lateral area of a right prism equals the perimeter of a base, just one of them, times the height. So LA is equal to PH. Okay? Where P stands for the perimeter of one of the bases, and H stands for the altitude. And you could kind of understand why they used H, because it means height. Okay, so that's not too bad. Remember, the formula for surface area was lateral area plus 2 of the base areas. Okay, so remember, and you might want to, I shouldn't say you might want to, write this one down. So the total area, in other words, the surface area of any regular prism, and this one, they're called, regular prisms are called right prisms. Of any right prism is the perimeter times the height plus 2 of the base areas. So P is for perimeter, H is for height. No, they call them altitude. And then 2 times the area of one of the bases. Make sense? Okay. For those of you that need to write down, what you're going to see this tonight for homework. Total area is synonymous with surface area, and total area is lateral area plus the base area. That's the logic of this. This is the actual formula. Okay. So you are in high school geometry, so if you were in pre-algebra, we do nice, easy, friendly ones. They're going to give you some challenging ones. So we'll do the two that we're going to do is going to be pretty challenging. Okay, but this is the easier of the two. So what kind of prism do we have here? We got a prism that it would, let's see, that's two parallel or two congruent sides here would be the trapezoid. So this is a trapezoidal prism. Okay, pretty complicated in where they put the numbers there. Notice they didn't label anything on the bottom trapezoid. That's because the bottom and the top are exactly the same. Just don't get into the habit of thinking the bases are always the top and bottom. If we turn this sideways or flip it around, it could be front and back, or it could be left and right. Okay, in this case, it's top and bottom. Notice I have all four sides of the trapezoid listed right there, 5, 6, 5, and 12. And then I have the height of the trapezoid, which is 4. And then lastly, I have the height of the prism, which is 10. You may want to rewind that and listen to that one again. All right, so we know that the surface area, or total area, as the book calls it, is that formula right there where P is the perimeter. Well, I can kind of figure that one out. Let's see, what's the perimeter? And remember, it's the perimeter of one of the bases. The basis here is a trapezoid. So let's see. If I go around counterclockwise, starting with 12, that would be 12 plus 5 plus 6 plus 5. Let's see, 12 plus 5 is 17, plus 6 is 23, plus another 5 is 28. And let's see, what's the height of the prism? H is the altitude, remember? That would be 10. Okay? Notice I did not use the 4 because that's the height of not the prism, that's the height of the trapezoid. Okay, so the 2 times B is 2 times 1 base area. So we got to go back to the formula for area of a trapezoid. Let's see, area of a trapezoid was that formula. I put it the way that you guys like it. Base 1 and base 2 are 12 and 6. The height is 4. Let's see, 6 plus 12 is 18. Half of 18 is 9. 9 times 4 is 36. Okay, so the area of one trapezoid is 36. Okay, but I need 2 of them. That's where that 2 comes involved right there. 2 times 36. Okay, so all this is just a little bit of evaluation here. That'd be 280 plus 72. And that's going to give me 352. And remember, surface area is a measurement of area, so therefore the units are squared. Well, there you go. There's a non-complicated surface area problem. Okay? All right, the second calculation, oh, by the way, that's half of what we're doing. It's just basic surface area, and the other half is volume. All right, so volume, the definition of volume is the amount of space in a 3D object. If you need a visual representation, if you take in this case, a rectangular prism, and you fill it full of little tiny cubes that are 1 by 1 by 1, length, width, and height, and then count the number of cubes, you got the volume. And that is literally what cubic units is. It's a measurement of how many cubes fit inside a shape. Okay? All right, so Theorem 12.2, another one that we're not going to prove because it's the obvious one, is the volume of any prism is equal to the base area times the height. If you can think about Post-it notes, right? If you took rectangular Post-it notes, right, and you measured the area of one of those and then multiplied it by how many of them you had, right, the height of the stack of Post-it notes, that would give you the volume, okay? Same thing if you had I've never seen triangular Post-it notes, but that's the way that would work as well too. But you do need one base area and then multiply it by the height. So we're not going to prove that one because that one's obvious. But there is your formula. V for volume is equal to 1 base area times the altitude, or the height of the prism itself. Okay? All right, so let's do the same calculation for this one again. Remember, this is the easy one. Let's see. So we need, for the volume, we need capital B, which stands for 1 base area times the height, or the altitude. So let's see, 1 base area. Do you remember what the area was of the base? If not, we do the calculation again. So let's see, base 1 and base 2 are 6 and 12. The height of the trapezoid is 4. 18, half of 18 is 9. 9 times 4 is 36. So the area of one trapezoid is 36. We take that and we multiply it by the height of the prism, in this case is 10. So we get 360 cubic centimeters. So there are literally, and this is from our book, there are literally what we just did in pre-algebra. So the 8th graders in pre-algebra, 7th graders as well too, literally just did these calculations for both surface area and volume. Well, this is high school geometry, so they're going to make it much more challenging for you guys. So we're going to do one just one. I can't give you an example of every single one of them. I fully anticipate a couple of you might send me emails on help on some of the homework, but let me show you what a challenging one looks like. So it says calculate the total area of the right. Wow, that was a lot of work. Some of the ones tonight for homework, they give the normal table thing where you simply do the calculation a bunch of times. Some of them are going to be a bit challenging. Some of them are going to involve special right triangles, but not too many of them. Okay, so just remember your calculations for special right triangles. Hey, we seem to be doing that special right triangle a whole lot. Well, just wait till we get to pre-calc. Algebra 2 uses it a little bit, but boy, does pre-calc and calculus use special right triangles. That's kind of why they hit it up really hard in geometry. Okay, so that concludes the class. As of taping this recording right here, you guys have not all taken your geometry test. Those of you that did fine. But if it turns out that somebody bombed it and wants to take a retake, just send me an email. I'll give you a reteaching and a couple worksheets to fill out to give you some practice if you want to take a retake. But maybe you all passed. I don't know. Hopefully you did. Okay. So that's Monday's class, and I'll see you guys on Wednesday.